Welcome you all in the lecture number 5 of Abstract Algebra MTL 6051. In this lecture, we will going to discuss order of the element, Cartesian product of the group, and the problems related to the Cartesian product of group, order of element in the Cartesian product of group, and group homomorphism and group isomorphism, and examples related to homomorphism and isomorphism. Let us see. If G is equal to U8, what is U8? How many element? U8 means how many elements relatively co-prime with 8 and 1 is less than x is less than 8 such that GCD of x and 8 is 1, right? How many element in U8? 1. GCD of 1 and 8 is 1, 3 and 8, 5 and 8, and 7 and 8. All GCD is 1. Therefore, U8 containing 4 elements, 1, 3, 5 and 7, in which 1 is identity. The order of 1 is 1, order of 3 is 2, order of 5 is 2, and order of 7 is 2, right? Why order of 3 is 1, 3 is 2? Since 3 into 3 is equal to 9 and 9 modulo 8 is equal to 1. Similarly, 5 into 5 is equal to 25. Modulo 8 is equal to 1, right? Then how many number of element of order 1 in U8? 1 element. And how many element of order 2 in U8? That is 3 elements. Similarly, U15. What is U15? 1, 2, 4, 7, 8, 11, 13 and 14. That is how many element greater than or equal to 1 but less than or equal to 15 which have GCD with 15 is 1, right? These are the element. These are total 8 element. Now see, the order of 1 is 1. Now 3 element in this group have order 3 and 4 element in this group have order 14, right? This is homework for you. Find all element of order 3 and 4 in U15, right? Now see, this you have already studied in BSc class, that if G be a group, then order of A is equal to order of x, A, x inverse. What is A and x belong to G. Order of AB is order of BA. Order of A is order of A inverse. If A to the power n is identity, then order of A divides n. If A belong to G, then order of A divides order of G, right? If D divides order of G, then it may or may not have an element of order D, right? See, if G1 and G2 are two groups, then we have to prove that G1 cross G2, which is as follows. G1 cross G2 is the ordered pair. A belongs to G1 and B belongs to G2, is group with respect to this operation, with respect to operation defined by this, right? See, if G1 and G2 be group, then certainly G1 and G2 have identity. We call E1 as the identity of G1 and E2 as the identity of G2, right? Then G1 cross G2, which is defined as follows, right? We have to prove that this G1 cross G2, this G1 cross G2 is group. For this, we have to show that closure law. Let us assume any two element of G1 cross G2, right? Let X is AB and Y is CD, right? Then X into Y, that AB into CD, and this defined as in this way. Why? Since this operation is already defined, ACBD. What is A? A belongs to G1. What is C? C belongs to G1. What is G1? G1 is group. Then AC belongs to G1 since G1 is group, right? Therefore it is closed. So AC belongs to G1. Similarly, B belongs to and B and D belongs to G2, right? Then BD belongs to G2, right? BD belongs to G2. Therefore, the ordered pair AC and BD belongs to G1 cross G2, right? Now, for the associative law, let X is equal to AB, Y is equal to CD, and Z is equal to EF. Then we can easily verify that X, Y, Z is equal to X, Y, Z, right? Now, what is E? E is equal to ordered pair, identity of the first group and identity of the second group, E1, E2, right? Then X dot E is equal to, what is X? X is equal to AB, right? What is X dot E? That is AB, E1, E2, and this is equal to AE1 and BE2. And what is this? This AE1 is A and BE2 is B. And what is this? This is equal to E. Means X dot E is equal to EX. It means E is the identity. This ordered pair is the identity of G1 cross G2. Similarly, for the inverse, let X is equal to AB belongs to G1 cross G2. Then A inverse belongs to G1 and B inverse belongs to G2. Then AB, A inverse, B inverse is A inverse, B inverse. This is E1 and E2, right? What is the inverse? Inverse of X is A inverse, B inverse, right? Then from above four property, we can say that G1 cross G2 is group, right? This is group. See another result. If G1, G2, Gn are the group, then Cartesian product of G1, G2, Gn are also group with identity E1, E2, En, right? For G1, G2, Gn, we have to A1, A2 and An, and another element B1, B2, Bn. Then the operation is defined by A1, B1, A2, B2, An, Bn, right? This belongs to G1 cross G2 cross G3 dot so on cross Gn. With respect to this operation, this G1 cross G2 cross Gn is group, and order of this is order of G1 into order of G2 into order of Gn, right? See one example related to this. If G is equal to Cartesian product of Z2 and Z4, what is Z2? Z2 containing two elements 0 and 1. Z2 containing two elements 0 and 1. And what is Z4? Containing four elements 0, 1, 2, 3. Right? What is this ordered pair? This ordered pair is 0, 0, 0, 1, 0, 2 and 0, 3. 1, 0, 1, 1, 1, 2, 1, 3. Right? This is Z2 cross Z3. Right? Find out the order of all element. 0, 0 is the identity, therefore order of this is 1. Right? 0, 1. What is 0, 1? We know that Z2 is group with respect to modulo 2. Right? And Z4 is group with respect to modulo 4. Modulo 2 means addition modulo 2 and addition modulo 4. This 0, 1. what is order of 0 1? 0 1 and 0 1, and what is the operation? Operation between this is from first pair modulo 2 operation and second pair modulo 4 operation, right? 0 plus 0 is equal to 0 and 1 plus 1 is equal to 2. Now and add 1 times this 0 1 again. Then first pair 0 0 is 0, 2 plus 1 is 3. Again add 0 1, right? And this is equal to 0 plus 0 is 0. What is 3 plus 1? 3 plus 1 is 4. 4 modulo 4 is 0. It means how many times we added this, right? 1, 2, 3, 4. 4 times. If we add 0, 1 plus 0, 1, sorry, 0, 0, comma 1, sorry, 0, 1, 0, 1 plus 0, 1 plus 0, 1, 4 times. Then we got 0, 0. It means order of this element is 4. Order of this element is 0, 2 plus 0, 2 is 0, 0. Order of this is 2. And order of this is 4. Order of this is 2. Right? Daughters 1. Then how many element of order 1? Identity element, 1 element. How many element of order 2? 1, 2, 3. 3 element of order 2. How many element of order 4? 4 element of order. Right? What is the total number of element? 4 plus 3 plus 1, that is 8. Now see, what are the possible order of element in Z2? That is 1 and 2. What are the possible order of element in Z3? That is 1 and 3. Then the number of element of all possible order in Z2 cross Z3. Number of elements of possible orders in Z2 cross Z3 is LCM of 1 1, LCM of this, LCM of 1 3. LCM of 1 1 is 1, LCM of 1 3 is 3, LCM of 2 1 and LCM of 2 3. LCM of 2 1 is 2, LCM of 2 3 is 6. Right? Then number of element of all possible order is 1, from here 1, 2, 3 and 6. Right? See, the number of element of order 1 in Z2 cross Z3 is given by, what is the LCM? LCM is 1 of 1 1. Then 5 1 and 5 1. This is 1. Number of element of order 2 in Z2 cross Z3. Where is 2? 2 is here. Then 5 2 5 1. 5 2 5 1. What is 5 2? 5 2 is 1. What is 5 1? This is 1. Number of element of order 3. Where is 3? 3 is here. Right? Then 5 1 and 5 3. 5 1 is 1. 5 3 is 2. Right? 5 1 is 1. 5 3 is 2. That is 2. Number of element of order 6. Where is 6? Here is 6. Then 5 2 5 3. 5 2 multiplied by 5 3. 5 2 is 1. 5 3 is 2. That is 2. Right? So all element 2 plus 2 plus 1 plus 1. This is 6 element. Total 6 element. Right? Now see the result. Number of element of order D in Zn cross Zm, that is phi d1 phi d2. d1 divides m and d2 divides m, and LCM of d1 d2 is d. Right? If number of element of order D in Zn cross Zm, see, this result is applicable. This result is applicable only for Zn cross Zm. Right? Only for Zn cross Zm. See this example. Z2 cross D3. What is Z2? Z2 is 0 1. What is D3? D3 is R0, R120, R240. Right? Then 0 R0, 0 R20, 0 240. And other elements of This D3 is 0FA, 0FB, 0FC. Similarly, 1R0, 1R120, 1R240, 1F of capital A small a, 1F of capital V small v, 1F of capital C small c. Right? This is Z2 cross D3. Order of element of Z2 is 1R2. Since Z2 containing two elements 0 and 1, order of 0 is 1, order of 1 is 2. Right? So possible order of element of Z2 is 1 and 2. And order of element of D3 is 1, 2 and 3. Right? Order of one order element is R0. Two order element is all reflection operation, means F of A, B, B, C, C. Right? And three element operation is R120 and R240. Right? Then how you evaluate LCM? LCM, make the pair 1 1, 1 2, 1 3, 1 1, 1 2, 1 3. Then 2 1, 2 2 and 2 3. Right? Hence Z2 cross Z3 has elements of order 1, 2, 3 and 6. Right? How many element of order 1 in Z2 cross D3? 1 element. How many element of order 2 in Z2 cross Z3? See, LCM of 1 2 is 2. LCM of 2 1 is 2. And LCM of 2 2 is 2. Right? Order 1 element in Zn or Z2, that is phi 1. And 2 element order in Z3, how many element of order 2 in Z3? 3 element, all reflection operation. The phi 1 is 1 into 3, that is 3. Phi 2 and phi 1. Phi 2 is 1 and phi 1 is 1. This is 1. Now see, phi 2. How many element in Z2 of order 2? That is 1 element, phi 2. Phi 2 is 1 into. How many element in D3 of order 2? 3 element. Right? 3 into 1 is 3. Then total 7 element. Total how many elements? 7 element of order 2. 1 element of order 1, 7 element of order 2. Order 3 element in Z2 cross Z3 is phi 1 and phi 3. Right? Phi 1 and phi 3. That is 2. Order 6. Number of element of order 6 in Z2 cross D3 is phi 2 and D3. That is 2. Now total number of element, this 2 plus 2 plus 7 plus 1. One identity element. Then 7 plus 2 9, 9 plus 2 11 plus 1. That is total number of element is. Now what is group homomorphism? Group homomorphism is if G1O1 and G2O2 be any two group, then the map phi from G1 to G2 is said to be homomorphism if it is operation preserving. Homomorphism is also known as operation preserving map. Operation preserving map. Operation preserving map. That is phi A of B1. See, between these two elements, operation of first group G1. What is the operation? O1. A, O1, B. O1 means operation of first element since AB belong to G1. This is equal to phi A. What is the element phi? If G1 is this and if G2 is this, what is A? A is phi A. And what is B? This B is something phi B. Right? Then what is AB? AB is somewhere here. What is the element of this? This is phi A and phi B. But see, this is G2. Here we apply operation O2. And here A of B means this is AB. Na? Between A and B, we apply operation of first group G1. A operation B. And phi A, phi B belongs to G2. Therefore, between phi A and phi B, we apply operation of G2. Therefore, due to this property, this group homomorphism is also known as operation preserving map. Right? And this is true for all AB belongs to G1. See the some example. If phi is a map from Z to 1, 1, what is Z? Z with respect to addition is group. Right? This is group. And this operation is defined as phi of n is equal to 1 and phi of n is equal to minus 1. 1 if n is even, minus 1 if n is odd. Prove that this is homomorphism. Right? Then there are three cases for Z. Even case, even odd case, even odd or odd even, both are same, and odd case. Right? See this example. This is even and this is even. Then phi 2n 2m is equal to phi 2 times n plus n. What is this number? This number is even. If this number is even, then this gives 1. Right? And this can be written as phi 2n is 1 and phi 2m is 1. 1 into 1 is 1. Right? So this case it is true. Phi 2n plus m is equal to, what is this? This is minus 1. Why? This minus 1 can be written as 1 into even odd is odd, 1 into minus 1. Right? What is 1? 1 is phi 2n. Since it is, if 2n is even, therefore this phi 2n is 1. And phi m is minus 1. Phi n plus m. What is phi n plus m? Phi n is minus 1. Phi m is minus 1. Right? Therefore, this phi map is group homomorphism. See another example. If phi is from general linear group of all matrices 2 cross 2, all entries are real to R star and defined as phi of A is equal to determinant of A, such that what is AB? AB belongs to GL to R. What is AB? AB is GL to R. Then what is phi? Phi AB is equal to, phi AB is equal to determinant of AB. Why? Since phi A is equal to determinant of A. And what is determinant of A? That is determinant of A into determinant of AB is equal to determinant of A into determinant of B. And this is equal to, what is determinant of A? Phi A. What is determinant of B? Phi B. It means phi AB is equal to phi A into phi B. Hence phi is operation preserving map. Operation preserving map, or phi is homomorphism. Right? Phi is homomorphism. Next, if G1 is equal to 1 minus 1 I minus I and Z2 is equal to 0, sorry, Z4 is equal to 0, 1, 2, 3, 4, right? Then these two groups are isomorphism. See, 1 minus 1 I minus I. This is 0, 1, 2, 3. What is order of 1? Order of 1 is 1. What is order of minus 1? In first group G1 we are talking about G1 and G2 say, or G1 and Z4. G2 is Z4. Right? Order of minus 1 is 2. What is order of I? This is 4. What is order of minus I? This is 4. Right? Similarly here, what is order of 0 is 1. What is order of 1? 1 is 4. What is order of 2? Order of 2 is 2. What is order of 3? This is 4, right? Then see, one element of order 1 in both group, one element of order 2 in both group, and two element of order 4 in both group. So one map with 0, so their order is same. -1 and 2 have same order, right? Then -1 map with 2. Similarly, this I map with 1. I map with 1 or I map with 3. Both are true. And -1 map with 3. Or first case is this 1 map to 0, -1 map to, and I map to 1 and -I map to 3. Now, and another example is that 1 map to 0, -1 map to 2, I map to 1 and -I map to 3. Sorry, I map to 3 and -I map to 1. This is another homomorphism and this is another homomorphism, right? It means these two are homomorphism. It is homomorphism, but later on we will see this is isomorphism also. See, the property of group homomorphism, the property you already studied in your BSc class. This is homework for you. Now see, what is group homomorphism? See the definition. If G1O1 and G2O2 be any two groups, then a map phi from G1 to G2 is said to be isomorphism if three conditions are satisfied. This phi is 1, 1, this phi is onto, this phi is homomorphism. It means 1, 1 onto homomorphism. This 1, 1 onto homomorphism is known as isomorphism. This is known as isomorphism, right? And if two group of isomorphic, then this G1 and G2 is denoted by this. Either this or this notation is also true. G1 or G2, right? These two group are isomorphic. See the example. If R plus set of real number with respect to addition and set of real positive real number with respect to multiplication are group, then phi x is equal to 2 to the power x, this thing is isomorphism. For this we have to show that this phi x is 1, 1, this phi x is onto, and this phi x is homomorphism. See for 1, 1. Let phi x is equal to phi y. Let phi x, 1, 1 case we already discussed in first lecture. Phi x is equal to phi y. What is phi x? 2 to the power x. What is phi y? 2 to the power y. Right? Then this implies that log of 2 to the power x to the base 2 is equal to log of 2 to the power y base 2. And this gives us x is equal to y. It means this phi is 1, 1. Now, for all y belongs to R plus, there exists x belong to R plus such that phi x is equal to y. What is phi x? Phi x is equal to 2x. Then, if 2x is equal to y, this implies that log of 2x to the base 2 is equal to log of y to the base 2, and this is x is equal to log of y to the base 2. What is this? This is a real number, right? This is a real number. Then this number belongs to R. It means for each y belong to R plus, there exists a real number such that phi of x is equal to y. Hence it is onto. Similarly, phi of x plus y is equal to, what is this phi x plus y? By definition it is 2 to the power x plus y. and this can be written as 2 to the power x into 2 to the power y. What is 2 to the power x? This is 5x. What is 2 to the power y? This is 5y, right? Then this is 1 1 onto and homomorphism. It means it is isomorphism. Right? See another example. Phi from set of real numbers with respect to addition and set of real number with respect to addition, and phi of x is equal to x cube is not an isomorphism. You have to prove that why it is not isomorphism, right? It is homework for you. Next, we have to show that U10 is isomorphic to Z4 and U5 is isomorphic to Z4. What is U10? How many numbers are relatively co-prime with 10 and which is less than or equal to 10? 1, 3, 7 and 9. This is U10. What is U5? 1, 2, 3 and 4, right? And what is Z4? 0, 1, 2, 3. This order of this 0 is 1, order of 1 is 4, order of 2 is 2, order of 3 is 4. Similarly, this order of 1 is 1, order of 3 is 3 into 3 is 9, and 9 into 3 is 27, and 7 into this order of 3 is 4, order of 7 into 7, that is 49 modulo, and this is equivalent to 9 into 7, this is 63, this is equivalent to 3 into 7, this is equivalent to 1, means order of this 7 is 4 and order of 9 is 1. Similarly, order of 1 is 1, order of 2, right? Order of 2 is 4, order of 3 is 3 into 3 is 9, that is 4, 4 into 3 is 12, 3 into this is 4, and order of 4 is 1, right? Sorry, order of 4 is 2, order of 9 is 2 also, sorry. Then see in these three groups, Z4 is isomorphic to U10, and this Z4 is also isomorphic to U5, right? And this U10 is also isomorphic to U5. Since the number of element of order 1 is 1, number of element of order 4 is 2, and number of element of order 2 is 1, right? Therefore, they are isomorphic. Now, you have to prove the property of isomorphism. This is homework for you. What is the property? Identity always map. This is G1 and this is G2. G1 and G2. This identity always map to identity of this group. If phi is isomorphism, then E1 map to E2. Phi of an is equal to phi a whole to the power n. If AB in G and AB commutes, then phi a and phi b also commute. Order of A divides order of phi of A. Sorry, order of A equal to order of phi of A. Right? If order of G1 is finite, and G1 and G2 have exactly the same number of element of every order, right? Sorry, if order of G1 is finite and G1 is isomorphic to G2, then G1 and G2 have exactly same number of element of the every order. See this last property here, right?